Welcome to this lecture on machine learning using Python programming. So, in the previous lecture we have started multiple linear regression and we have seen the two important problems that may occur if we talk about multiple linear regression, and these two problems we have seen. One is collinearity, and then using variance inflation factor we can find whether there is a case of collinearity in our data set, and if it is there, how to mitigate that. And then we have seen what are the confounding variables and how to find out these confounding variables effects and how to mitigate them. So, we have seen if there are some confounding variables, then we can use a technique like stratification or matching. So, in this case we create two different data sets, or we divide the data set in two separate groups, and these groups are comparing similar groups. So, basically we have seen the example of exercise and weight loss. So, weight loss we want to find whether there is weight loss depending on the exercise, and in that case calorie intake may be confounding variable. So, how we can analyze, how we can mitigate this situation? In that case we can now have one this confounding variable as a feature. Calorie intake we will again take as a feature in our model, and then we can create two parts. One part will contain all those instances where calorie intake is low, and another part will have the instances that where the calorie intake is high, and then so these are called as the strata. So, we are dividing the data into subgroups, these are called as strata, and based on the level of confounding variables we are creating them, and then we are examining relationship between independent and dependent variable within each these stratum, and then we will try to generalize relationship by combining results of each stratum. So, this is the example. Now, we are taking another example where we can see the effect of confounding variable, and then how using stratification we can take care of these confounding variables. So, suppose we want to study the effect of a new drug on blood pressure reduction. So, blood pressure reduction is a dependent variable and new drug is independent variable in this case, and we can suspect that gender is a confounding variable because this gender influences both drug response as well as baseline blood pressure levels also. So, in this case gender is the confounding variable, and how we can address this. So, we will stratify the data in two groups based on the gender. So, one group of data where all males are, and another group where all the females. So, then we will analyze the effect of drug on blood pressure separately within the male group and female group, and then we will compare results of these two, and we will try to check the effect of drug is consistent across genders or not. So, if it is not consistent, in that case gender is a confounding variable. So, now testing significance of independent variables. So, regression analysis allows us to test for significance of relationship between independent variable and dependent variable while controlling for other factors. So, we will see that there are statistics, and so that is t statistics and p values. Using these we can find out whether one independent variable is significant in our model or not. So, significant in the sense whether response variable is depending on this predictor or independent variable or not. So, why we are doing this? sometimes we have a large number of features, large number of independent variables, and we are trying to build our multiple linear regression model. So, in that case, if we will take all these features in our model, and few of these features may not be significant. So, it means your dependent variable is not depending on these features. So, in that case it will make your model predictions wrong, or we say like this, if garbage in garbage out, means if your input is wrong, and then definitely your output will also be wrong. So, you will need to take care of your data set. In here basically we are trying to check whether all these independent variables are important to include in the model or not. So, using multiple linear regression, using p values, we can check whether the variable is important or not. So, certain variables predict the behavior of the dependent variable, and other variables may not predict the behavior of dependent variable. So, we should leave those variables, those independent variables. So, let us see what is p value, and then how using p values we find which independent variables are important, or they explain variability in the response variable. So, first of all we talk about null hypothesis and alternate hypothesis. So, generally the null hypothesis is independent variable is not statistically significant and likely important in the regression model. So, the p value is the probability of obtaining the observed results or more extreme results given that the null hypothesis is true. So, this p value helps us to access the strength of the evidence against the null hypothesis. So, we can say that if p value is low, and typically if it is less than equal to 0.05, so low p value indicates strong evidence against the null hypothesis. So, suppose p value is 0.02, then we can say that there is 2% chance of observing data assuming the null hypothesis is true. So, it means there is only 2% that the hypothesis is true. Your data set, your data is like that, only 2% of the data is according to the hypothesis, null hypothesis, and that is why if value of p is less, in that case you should reject null hypothesis, and you will in that case conclude that the variable is important. So, independent variable is important and you should include that variable in your model. And high value, high p value, so typically if it is greater than 0.05, so high p value suggests weak evidence against the null hypothesis. So, it means independent variable is not statistically significant, and in that case it means it is not important to include in your model. You should leave that independent variable for which p value is high. So, we can say that if p value is 0.30, so it means 30% chances of observing data assuming that the null hypothesis is true. So, this will lead you to fail to reject the null hypothesis and suggesting that the variable may not be significant. So, here we can see one example. So, suppose east, south and north that are different independent variables, and when we will run multiple linear regression model, we will train this multiple linear regression by taking east, south and north as independent variables, and as a result you will get some t statistics and p values. So, here you can see p values is less for few independent variables and high for other independent variables. So, we have already seen that p value for each term tests the null hypothesis, that the coefficient is equal to 0 or not. So, if it is less than 0.05, it indicates you can reject the null hypothesis. So, and our null hypothesis was that that variable is not significant. So, it means that variable is significant. So, and if the predictor that has low p value is it means it is likely to be meaningful addition to your model. This variable you should add in your model, and conversely the large p value. So, in this case 0.092 is a value that is corresponding to yeast. So, this variable is this p for this corresponding independent variable p value is high. So, it suggests that the change in the predictor are not associated with this independent variable yeast, and that is why we can leave this independent variable. So, now in this way, by seeing the p value corresponding to each independent variable, we can build our multiple linear regression model. Means we have large number of variables, and if we are not knowing exactly which variables are important and which are not, although we have seen that through the literature we can find out which variables are more important. So, definitely we can include those variables, but for the rest of variables where we do not have any idea whether these are important and not, then we can use these p value, and using this p value we can find out whether to include that variable in our model or not. So, there are 5 methods of building the model. First is all in, then backward elimination, forward elimination, bidirectional elimination, and score comparison. So, these are the stepwise methods, stepwise regression that suggest us how to build the model, or which independent variables finally we should include in the model. So, backward elimination technique of building a model. What is this? First of all, we select a significance level to stay in the model. Means to stay a independent variable in the model, we need to select a significance level. So, that is suppose 0.05. Then fit full model with all possible predictors. So, you take all the independent variables, all the predictors in your model and fit your model. Then consider the predictor with the highest p value. So, you check for which independent variable the p value is the highest, and if that p value is greater than this significance level, then you will remove this predictor. Otherwise, you will stop here, your model is prepared, because the highest p value is not greater than the significance level. So, it means all other variables are also important. For all other variables p value is less, and that is why those variables are important in our model. So, we should keep all those variables. Otherwise, what we will do, if its highest p value is greater than significance level, we will remove this predictor, and again we will fit the model with the remaining predictors. We will remove this predictor, and with the remaining predictors, remaining independent variables, we will fit the model, and again after fitting the model we will find a predictor with the highest p value, and again we will check if p is greater than this significance level. Again if it is greater than significance level, we will remove this predictor and will do the same in different iterations. So, this is the backward elimination model, and finally, when you will stop removing these predictors, your model is ready. Model is ready means you have identified which independent variables are important, and those independent variables you will consider in your model. Forward selection is the another method. In this selection method, we select a significance level to enter in the model. So, initially we are not having any variable in our model. So, to enter a variable in our model, independent variable in our model, we will take some significance level. So, that significance level is suppose 0.05. Then fit all simple linear regression, so it's initially simple linear regression model, because there will be only one variable, so independent variable. So, you will fit all simple regression models, So, there are chances that there is no linear relationship between independent and dependent y and xi. So, we are saying that we will fit all simple regression models, it may be linear or non-linear, and then select one with the lowest p value. So, you will consider only that variable finally in your model that has the lowest p value, then keep this variable and fit all possible models with one extra predictor. So, this variable is now final in your model, and you will fit all many other models by taking one extra predictor, by adding one more extra predictor in your model. So, and then you will after fitting these models, you will consider the predictor with the lowest p value, and if this p value is less than the significance level, you will again add again do the step number 3, means now 2 variables are decided, are added in your model. So, we will take one by one, we will take remaining predictors, and in this so several models we will fit by taking these extra predictor in these 2 predictors that have already been decided. So, this we will do until there is no more variable we can add, or after adding the variable its p value will be greater than significance level. So, you will stop at that time. Then there is the next method of building the model, that is bidirectional elimination. So, in this case we select a significance level to enter in the model and another significance level to stay in the model. So, there are 2 significance levels values, significance SL enter. So, suppose that is 0.05 and significance level that stay in the model 0.05. Then perform the next step of forward selection. So, we are trying to find out which predictor we should add in our model, and new variable we must have if p is less than p enter. So, we will include that variable in our model, and after including the next model using step number 2, we will perform all steps of backward elimination. So, old variable must have p less than significance level of stay. So, if it is p less than this, then old variables we will keep in our model, otherwise we will remove those. So, we will perform all the steps of backward elimination in step number 3, and then again we will go to the step 2, we will try to add a new predictor, and after adding a new predictor we will perform the steps of backward elimination, and so we will do it several times, and we will stop when no new variable can enter and no old variable can exit. So, in the second step we are not able to add any variable, and in the third step we are not able to remove any variable. So, then this process will stop and your model will be ready. So, the next method of building model is all possible models or score comparison. So, what we do here, we select a criterion of goodness of fit, that Akaike criterion. We will see what is this Akaike criterion. So, what we do in this method, we will construct all possible regression models. So, if there are n independent variables, total 2 to the power n minus 1 total combinations of these independent variables we can form, and we will fit our model for each these combinations. So, total 2 to the power n minus 1 possible regression models we will construct, and we will select one with the best criterion. So, we will calculate Akaike criterion or any other criterion to check the goodness of our model, and based on the that criterion, whatever model is the best model we will keep that model. So, this is practically not possible, because it will take lot of time, lot of computation. So, if there are 100 features or 100 independent variables, 100 predictors in your data set, so it means 1, 0, 2, 3 models you may have. So, it is practically it is not possible, but we can do this like this. So, let us see what is AIK information criterion or AIC. So, using AIK information criterion also we can compare different regression models. So, this is a widely used metric for assessing the goodness of fit of a statistical model, while also considering complexity of the model. So, why AIK information criterion is important metric for checking the goodness of the model, because it considers complexity of the model also, not only in terms of predictions, but of course, we are considering what is the prediction of the model, how much correct predictions are there, but we are considering complexity of the model also, because if your model is complex, in the previous lectures, starting few lectures we have seen, if model is complex, there are chances of overfitting. So, we do not want more complex model. So, AIK is basically giving you balance between correct predictions and model complexity, because otherwise your model may work very well on the training data, and but you do not have the new data, or you do not know how well your model behave for the new or future data. So, it is particularly useful in model selection, where goal is to choose the model that best balances fit and complexity. So, how fit your model, how well your model is fitting the data, and what is the complexity of model. Both of these two are included in AIK information criterion. So, AIC is defined as 2k minus 2 log of L. So, what is this? K is the number of parameters in the model. So, we know if the number of parameters in the model is large, that much complex your model is. So, K is basically giving you the complexity of the model. So, L, what is L here? 2 log of L. So, L is a likelihood of the model. So, it measures how well the model explains the observed data, or how well it fits the observed the data set. So, likelihood L is the probability between 0 and 1. So, first term is dealing with the complexity of the model, and second one is dealing with the fit of the model, how good how good of the fitness. So, first term you can say penalizes the model for having more parameters, or it is penalizes complex models, so which discourages overfitting. And second term, it rewards the model for better fit. So, if it is better fit model, so it is giving the reward, and using the first term, if a large number of parameters are there, so it is penalizing the model. So, how we can now interpret AIC? So, lower AIC values indicate better models, because lower AIC means your first term is low and second term is high, and since there is minus sign between these two, so minus sign you can say that 2k plus minus of this second term. So, in this way your total AIC value will be low. So, if lower AIC values indicate better models. So, you can say that a model with a lower AIC is generally preferred, because it suggests a better trade off between model complexity and goodness of the fit. So, we have seen in today's class different ways of model building. So, using p values, we can use different methods like forward selection, backward selection, or bidirectional elimination. So, using these methods we can build the model, and then there are different metrics through which we can evaluate if more than one models we have. Suppose if we are considering 3 features, or we are considering 5 features, or we are considering 10 features, and then we are trying to check which model is better. So, in that case we can use Ekike information criterion. So, we have seen this also. So, this Ekike information criterion we have seen, it keeps balance between complexity of the model and goodness of fit of the model. So, this is related to multiple linear regression, because multiple linear regression, in that case there will be large number of variables, few of them may be important, few of them may not be important, and the number of variables that we will include in our model, it will make the model more complex also. There may be chances of overfitting. So, in that case we will need to first of all build the model by using, we can use these techniques of checking which variables we should include in our model, and then removing the variables. So, using forward selection or backward selection and so on. And then finally, after building the model, we can check the AIC value of the model, and if it is low, then we will say that the model there is a good balance between complexity as well as fitness of the model. And if it is value of high, so we should take some other model, or other model in the sense where number of variables or variable features are different. So, this is all about multiple linear regression. In the next lecture we will see polynomial regression model. Thank you.